state method. You also copy down these notes. So your first chapter is only the theoretical chapter, and then only numericals are there. Okay. So the theory will be asked from this unit only for the examination. So now for the limit state method, I can write it is method of design which is which is further improved which is further improved from ultimate load design. Okay, so copy down this about the limit state method. So in short, we will look for the two types of limit state method, and those two types are we have discussed in last lecture, I think so. So you are not telling how far we have completed. So I have assumed that it is discussed in the last lecture. So limit state of collapse and limit state of serviceability. These are the two types. So first it is limit state of collapse. Limit state of collapse. Okay, first is limit state of collapse. So now here in the limit state of collapse, the design, write down first, the design based on based on limit state of collapse collapse provide provide necessary safety necessary safety of of the structure of the structure against against partial or total collapse of structure. Okay, so it says that the limit state of collapse, it provides the safety for the structure. Okay, when the condition occurs, that is the partial or the partial or total collapse of structure is taking place, so it provides the safety. Limit state of collapse safety means what? When you design the beam, column and slab by using this approach, then what happens? Before failure, these members gives you the sign. ओके, म्हणजे हे जर फेल झाले, if these members fails, they won't fail suddenly. Means what? Now suppose now beam is there, and suppose the capacity of the beam is to carry a load of 100 kilonewton. Okay, and if the 150 kilonewton load is acting on that beam, okay, so in the case of working stress method, as soon as the load increase, as soon as it becomes 150, or instead of 100, if 150 load is act, the structure will collapse immediately. Okay, structure will collapse immediately. But in the limit state of collapse, it provides you the safety against this partial and catastrophic collapse. Okay, so it will give you the sign. Some cracks will develop, then what we can say, some bending will occur, and after giving these multiple signs of failure, then that structural member fails. Okay, so this is what is the meaning of this. Then next is, it is possible. Continue further. It is it is possible. It is possible to assess. It is possible to assess the collapse limit, the collapse limit, which may be which may be due to various effects, various effects of of overturning, overturning, sliding, sinking, etc. Okay, so it basically, it can give you the collapse limit. Okay, it can, the limit state of collapse will give you the collapse limit for what? For the factors like overturning, sliding, sinking. So many factors are there. Okay, so these are some of the names given over here: overturning, sliding, sinking, etc. Okay, so the limiting value, this limit state of collapse can give you the limiting value for that structural member for the this overturning, sliding, sinking. Okay, normally this overturning, sliding is there in the case of retaining walls or the dams, big structures. Okay, and then sinking is occur in the beams. Okay, settlement sinking, that can be occur in the beams also, in the columns also, in the foundation. So the, for the sinking limit of the beam or the foundation or the any other structural member, that can also be designed by this limit state of collapse, or this limit state of collapse gives us that value, what is the allowable and permissible value of that. Okay, then the next is limit state of serviceability. Okay, so next type is limit state of limit state of serviceability. Okay, so let us see what does this says. Now I will write, you copy down it. It is related to the performance of structure structure. It is related to the performance of the structure, full stop. It is introduced, it is introduced it is introduced for serviceability serviceability, it is introduced for serviceability and and various limits various limits and for the various limits, here for the is remaining, you write down for the various limits of deflection deflection, then cracking, vibration, etc. Okay, so this serviceability is related to the performance of the structure. So how the structure is stiff. Okay, so what is the maximum deflection occurring in the structure? What is the cracking pattern? What types of cracks are developed in the structure? That the limiting value for this is provided by the limit state of serviceability, or all these things comes under the limit state of serviceability. Now the vibration. Now vibration, it comes under the what we can say. Suppose now instrument, under the instrument. Suppose now you are designing a slab, okay, that is on the first floor for industry, and on that slab now suppose a machine you are going to build a machine, okay, and that machine will produce some vibrations, okay, and due to that vibrations, whatever slab you have designed below that machine, it may get cracked or it may get collapsed, okay. So such a type, so it doesn't come if it is get collapsed, then there is a very bad serviceability, but it should not get collapsed due to this vibration also, okay. So that limits, all these limits are governed by this limit state of serviceability. Okay, so in short, I have told you what the things which are considered in limit state of collapse, and what are the things which are considered in limit state of serviceability. So in short, also you keep this uh, as your notes, because this also required for your competitive examination also. Okay, so now after that we will look one term. That term is known as load factor. Okay, so the next definition we will look for, okay, and it is called as load factor. What is the meaning of load factor? Okay, so I will write down the definition, you also copy down this. The ratio of, it is the ratio, okay, the ratio of ultimate load, the ratio of ultimate load to the working load is called as is called as load factor. Load factor, and this is also our factor of safety. So if you write down in mathematical form, then it is load factor is equal to, what does it says, it is the ratio of ultimate load divided by working load. Okay, generally we use the notation WU for this, and generally we use the notation W for the working load. Okay, I hope now you are understanding these things. So here you can see this load factor, or this is also the factor of safety. and it is nothing but it is the ultimate load ratio of the ultimate load to the working load. Now how this load factor is calculated? Suppose now let us take the example in the last lecture. Suppose a structure is uh, under a load of structure is having a working load of 100 kilonewton. Okay, and the ultimate load on the structure is 150 kilonewton. So the maximum load, suppose 150 kilonewton comes on the structure, then the load factor will be 150 by 100, that is 1.5. If you are not understanding, I will write here somewhere. Okay, so ultimate load is suppose now 150 and working load is 100, then your load factor will become 1.5. This is our factor of safety. So what we always do in the limit state of design, generally what we do, we multiply the working load by the load factor. Okay, suppose now a structure carries a working load, W means working load of suppose now 1000 kilonewton. Okay, 1000 kilonewton load. Suppose now this 1000 kilonewton load is acting on any column. A column is there, and on that column, suppose this 1 kilonewton load is acting. Then, while designing that column, what we generally do, we calculate the ultimate load, and that ultimate load generally it is calculated by 1.5 times into this 1000. Okay, and we design that column for 1500 kilonewton. So even though on that column, okay, so even though on that column the load is coming is 1000 kilonewton, but still we design that column for 1500 kilonewton. Okay, for instance, I am telling you, assume it is column. It may be any structural member, okay, which carries a load of 1000 kilonewton. But while designing by limit state method, we will design it for 1500 kilonewton. So we will design it for little bit on higher side. Okay, so it will gives us the better serviceability. Suppose now in future, due to the wearing and tearing of the structure, and if any other load increases on the structure, suppose now in future instead of this 1000 kilonewton, if the load is increased and it becomes 1300 kilonewton, still this structure won't fail. Okay, if we design by this limit state method. Okay, we this is the load factor. This also we consider here in this method. So the next point is characteristic load. Okay, characteristics characteristics load. So what does it mean, characteristics load? So first write down the definition, then I will tell you what does it mean. It is it is the value of it is the value of load which which has which has 95% probability probability of which has 95% probability of not being not being exceeded during during life of the structure. So very simple definition is there, during life of the structure. Okay, so characteristics load. What does it mean? It is the value of load which has a 95% of probability not being exceeded during the life of the structure. Now suppose any structure is there. Suppose now 1 BHK residential bungalow is there, and if you consider the top slab, okay, top slab, where on that slab the above it terrace is there and coba is there on above that slab. Suppose now the maximum load is considered as 100 kilonewton. Okay, and right now the slab is designed for the load of suppose now 70 kilonewton. So we call that 70 kilonewton load as a characteristics load. Okay, if it has a probability of it is not getting exceeded 95%. Okay, so that load is called as a characteristics load. So if you don't understand this, then I will give you one more example so that you will understand it. Suppose now M20 concrete is there. Okay, now you will understand this. Suppose now M20 concrete is there. Then what does this 20 represents you? This 20 represents grade of concrete, right? This 20 represents grade of concrete. What does it exactly mean? 20. What does it exactly mean? हे 20 म्हणजे काय आहे? So it is nothing but strength in 20 MPa. You will tell me. Then it is nothing but 20 Newton per mm square. Okay, so it says that for 1 mm square area, the strength is 20 Newton basically. But how this value comes? When this strength is called as characteristic strength. Okay, तर याचा अर्थ काय की suppose now in a lab, suppose you have casted 100 cubes. Okay, likewise 1, 2, 3. If you have casted 100 cubes, how many cubes? 100 cubes. You know that standard cube size is 15 by 15 by 15 in centimeter and 150 mm by 150 mm by 150 mm. Suppose now you have casted 100 cubes in the concrete lab and you started testing these cubes on CTM, compression testing machine. Okay, if you start to test it, so out of these 100 cubes, if 95 cubes gives you the strength of this 20, then this 20 is called as characteristic strength. Okay, and the load corresponding to this characteristic strength is generally called as characteristics load. Are you getting my point? So that is your first cube. Suppose it gives you the strength of 21.29. Second cube it is 20.09. Third cube suppose it gives 17.18. Likewise 100th cube it is give you 20.05. Okay. So if the 95 cubes gives you the strength 20 or above 20, okay. So for M20 grade of concrete, then this 20 is nothing but your characteristic strength. Okay, and the load corresponding to that strength is nothing but in generally characteristics load, and the characteristics load has a probability. म्हणून तर इथं आपण 95 घेतलंय ना. 95 by 100 means what? 95 100 means what? It is 95%. Okay, so it is having a 95% of probability. So if the load is there, then it will not exceed during the lifetime of structure. It is having the 95% probability. Okay, so this type of load is called as characteristics load. Also I have explained you what is the characteristic strength. In this case now, if you tested 100 cubes of M20 grade concrete and out of 100, if 95 cubes gives you the strength of 20 Newton per mm square, then that 20 is called as the characteristic strength. Okay, this is the example for that. Now technically we will see the definition. The next point is characteristic strength. Characteristic strength. Okay. So now it is the strength of it is the strength of concrete block. It is the strength of concrete block concrete block which is given by the ratio of by the ratio of characteristics load per unit area. You know that load per unit area is nothing but stress. Okay, that is the strength. Is called as is called as this characteristic strength. Okay, or it can be also written as it can be also written in as so ह्याला or आहे बरं का ते. I can write it is a value which have which have 95% of probability 95% of probability probability of not being exceeded of not being exceeded not being exceeded during life of structure during the life of the structure. Okay, so what the definition tells us, characteristic strength. So simply, if you take this characteristic load and you divide it by unit area per unit, divide it by area, cross-sectional area, then you will get this characteristic strength. This is the one thing. Second thing is that it is the value which have 95% of probability of not being exceeded during the life of the structure. Same it is as of the characteristics load. It is also the 95% probability. So M20 grade of concrete now. So for M20 so it is the value which is having 95% of probability. Okay, correct. In reverse, you can also say that this 5% of test results should not expected to fail. Okay, so the not more than 5% of test results are expected to fail. So one and the same thing. If you use the 95% probability of success, then there is a 5% probability of failure. Okay, so these types of loads are nothing but this. These are the characteristic strength. Okay. So now we will take the next point. Now some load combinations are there. Some load factors which are used in some different load combinations. So I will tell you that table. I will write here that table. You copy down that table. Okay. So load combinations. Load combinations and factors. So first, here I will give the heading load combination. You need to write down it in a tabular form. Okay, load combination. So in the load combination, there is a dead load, then live load, and wind load or earthquake load. So this is for first is limit state of collapse. and for limit state of serviceability for the limit state of serviceability. Again, we will divide it into three columns: dead load, live load, and wind load. So here the first load combination is dead load plus live load. Dead load plus live load. So the factor for dead load it is 1.5. For live load this is also 1.5, and for this wind load it is 1. So we multiplying the dead load by this. Okay. Then in the limit state of serviceability for dead load it is 1. I will tell you how to use this while solving the problem. Okay, just now for time being you write it down. Okay, and there is no factor for wind load. So as it is we are going to take it. Next combination is dead load plus wind load. Okay, so the combination here it is 1.5 or 0.9. Okay, depending upon the condition factor is used. Then for live load no factor is given. These are the standard values given by IS 456 2000. Okay, you remember this. These are the standard values given by this IS code. You will get this table in the IS code. Okay, and some one paragraph is also given. Read that paragraph. So 1.5. Then here for dead load it is 1. Again no factor is given for the live load. Here live load is not there. So 1. Okay. And now the third case, dead load, live load and wind load. Load plus live load plus wind load. So the factors are 1.2, 1.2, 1.2, and here 1.0, 0.8, 0.8. Okay. And important note is there. So note is that while considering the earthquake load, replace wind load by earthquake load. Okay. So while considering earthquake load, replace replace wind load by earthquake load. Okay, so we won't consider wind load and earthquake load in the same combination, or at a time we won't consider this because both the loads are having very high values, and if we started to design the structure by using these two loads, then the dimension would have been far more larger than what we see today now. Okay, normally today our beam is now width is 230 mm. Actually, for the residential building up to G plus 3, the design won't change. Normally the beams are 230 by 230, 230 by 300, 230 by 350. Okay, this type of standard design is there. That is because while designing the G plus 3 structure, we consider the earthquake load. We won't consider the wind load at that time. Okay, and while designing the roof truss, okay, or any industrial shade, on that we consider the wind load. Okay, earthquake load we won't consider on that. So that therefore at a time either we are going for the wind load or we are going for the earthquake load. So this is the table which is the important one, and how to use that and where we are going to use that we will see while solving the numericals. Okay, that is later on we will see that how to use that. So the next is the design value. Okay. Next point is the design value. What is the design value? So it is it is ratio of it is a ratio of characteristic strength characteristic strength of material to the partial safety factor to the partial safety factor is called as is called as design value. So the decision of this design value. So this design value is it is nothing but it is a ratio of the characteristic strength of the material to the partial safety factor. Okay. Now mathematically it can be written as FD. FD represents design value, which is equal to this F divided by this F divided by gamma M. Okay. So I will write what is F, what is gamma M. So here I will write where FD is nothing but this is design value. Design value. Okay, this F, it is nothing but it is characteristic strength, and this gamma M, it is nothing but this is the notation for partial safety factor. Partial safety factor. Okay, partial safety factor of material. So now the most, so this is very simple formula. I think there is nothing much more difficult in this. So FD is the design value, which is equal to F divided by gamma M. F is nothing but this is your characteristic strength, and this is the partial safety factor of the material. If you take the ratio of characteristic strength to the partial safety factor, then it gives you design strength. Okay. So now the values of partial safety factor for steel and concrete. Okay. So safety factor partial safety factor for concrete. So for concrete, it is represented by gamma C. Okay, and for concrete, its value is 1.5 partial safety factor. Okay, and partial safety factor for steel, partial safety factor for steel, it is gamma s. The notation is gamma s, which is equal to 1.15. So these are the partial safety factors for steel as well as for concrete. Okay, so write down all these things. These are some basic things which I have told to you right now. So in the next lecture, we will go for stress block parameters of limit state method. Okay, stress block parameters. Now from the next lecture, it is very important. Now till now, just theory part was there. This theory part is not much. I think now it is not much more difficult. If you read it once, you will get the things clearly. But now from next lecture onwards, now the first lecture is very important, the stress block parameters of limit state method. So from here actually you will come to know what type of forces are we need to consider in the limit state and what are the criteria in the limit state. Okay, how the stress block diagram is drawn, how the strain diagram is drawn. Okay, so very important things are there which we are going to see from the next